the chat box. All right, so today we're going to talk about a new type of algorithm called local search algorithms. Okay. And to introduce this local search algorithm idea, I'm going to start with an algorithm which I think many of you have seen before. Which is gradient descent. Okay, so gradient descent is basically gradient descent is a way to optimize a function in a continuous setting. Right, so if you have a function which has a bunch of variables, and the variables can take any real values, let's say, right, then you can use gradient descent to optimize that function. So basically, gradient descent is, if you have a function, let's say a 2D function, which is something like that. Okay, so that's not a great drawing, but it's some sort of function. And then gradient descent is that you start at a point, and then you basically you keep going in directions which makes your function smaller. Okay, so suppose you're trying to minimize this function, then you keep going in these directions that make the function smaller until you get to some point where around the star point, like all of these surrounding points around the star, they might all be larger than the star point. Okay, and then you stop at that point. So that's gradient descent. And this is usually used in a continuous optimization setting. However, today we're going to look at how gradient descent can work in a discrete optimization setting. Okay, so discrete optimization simply means that, whereas in traditional gradient descent in the continuous setting, you can basically, if you start at this point x, what's happening? All right, if you start at this point x, you can move into any of these surrounding points, right? You can move over here or any point you want, okay? Now, the difference in the discrete setting is that if you start at a point, right, then, why is this zooming all the time, right? Sorry, 1 second. Yeah, it's supposed to not zoom. But anyways, right, so if you start at this point, jeez. All right, I'm sorry about this. Okay, let me try going slower. Okay, you start at this point x, all right? And then you're not allowed to move to any of the neighboring points. You can maybe only move to a few of the neighboring points, right? Because we're in this discrete setting, okay? You can only move to, let's say, if you're in a 2D setting, you can only move, let's say, up, down, left, or right. Okay, if you're in a 3D setting with 3 variables, you can maybe move in 8 different directions, okay? And if you have n variables, you can move in, let's say, 2 to the n different directions, okay? But you can't move in arbitrary directions. So that's the main difference between discrete and continuous gradient descent. And now the thing about gradient descent is that when you make a move from this initial starting point to some nearby point, right? You have the sense of distance between the points. So for example, you can only move from this point to one of these surrounding points, right? You can't directly jump from the starting point to like a very far away point. Okay? So there's a sense in which points can be neighbors of each other. So all of these little x's are neighbors of the big central x. Okay, so this is the main property about local search, which is that what we're going to do is we're going to start at a point, and then we're going to define this neighborhood relationship, which is another set of points which are close to this point. And then we allow ourselves to move to any one of these neighboring points. And usually, when you apply gradient descent, the neighbor that you select is any neighbor which can improve your objective function. So suppose you're trying to minimize the function, then you can go to any neighbor which has a lower objective function. Okay, because some of your neighbors might have higher objective functions, so you do not go to those neighbors. You always move to a neighbor with a lower objective function. Okay, so to sort of apply this to one example problem, let's consider the vertex cover problem we talked about last time. Right. So remember that what we have is you have a graph, okay, and then you're going to pick a subset of the nodes such that you want to cover all of the edges in the graph, right? And by covering an edge, I mean that if you have an edge like this, right, u and v, you have to pick either node u or node v, and that's going to cover up this edge. Okay, so we saw a bunch of ways to solve this problem last time. And today, just as an example of applying gradient descent to this discrete optimization problem, we're going to see how to apply local search on this. Okay, So the first thing we need to do is to define this neighborhood relationship. Okay. And here, the points that we're going to consider are possible solutions to the vertex cover problem. Okay, so here S is one possible solution to vertex cover. And when we say possible solution, we mean that it's got to be a subset of points which actually covers all of the edges in the graph. Okay, and S prime is also a possible solution to the graph. Okay, so S prime also needs to cover all of the edges. Okay. And we're going to say that these two solutions, S and S prime, are neighbors of each other if S and S prime differ in only a single node. Okay, so for example, if you have a graph like, I don't know, like this, okay? All right, so, so this is not such a good graph. All right, but never mind, I'm not going to draw the example, okay? So what I'm trying to say is that S is a set of nodes, and S prime is another set of nodes, and S and S prime are neighbors if they differ in only one node. Okay, so you can either add a node or delete a node from S, and then you'll get S prime. Okay, so that's our neighborhood relationship, right? And notice that each vertex, S has at most n neighbors. Okay, because you have, let's say, at most n nodes in the graph, and so you can at most add or delete any one of these n neighboring nodes. And that produces all of the neighbors of S. Okay, so then once we know about the neighbors of S, which neighbor are we going to move to? Because this gradient descent is all about moving from one node to a neighboring node, to another neighboring node, and so on until you stop eventually. Okay, and so in gradient descent, the way that we select a neighbor to move to is that you can move to any neighbor S prime, which is also a vertex cover, and which is a smaller vertex cover, because we're trying to minimize the number of nodes we use to cover the entire graph. Okay, so if currently you cover the entire graph using S, then you can move to any neighbor S prime, which also covers a graph, but uses fewer nodes. Okay, and then you can just keep doing this until eventually you get to some point S, and maybe all of the neighbors of S either do not cover the graph, or they're larger than S. Okay, if you get to that point, then S doesn't have any better neighbors than itself, right? Because any neighbor either doesn't solve the problem because it doesn't cover the graph, or it uses more nodes. And so in that case, S is a locally optimal solution. Right, now one thing is that this algorithm is very fast, okay, because it terminates in at most n steps. Because if you have a graph with n nodes, right, then since we always insist on moving to another neighbor which has lower cardinality, right, so S prime has fewer nodes than S, okay, then at most you can take n steps, right, because you can start with maybe all n nodes, and then each time you remove one of these nodes, and so after n steps you stop. So this is a very fast algorithm. Okay. However, the point of this algorithm, the problem with this algorithm is that it will not necessarily find an optimal solution. Okay, so we can look at a few examples of this. So for example, in the first graph over here, right, one solution that this gradient descent might produce is that it might take all of these outside nodes. Okay, and the reason this is a local optimum is because if you suppose this is your current solution S, okay, then there's no neighbor of S which actually improves on S, because any neighbor of S differs from S by only one node. Okay, so suppose you take one of these nodes out. Okay, but then once you take a node out, it no longer covers the entire graph. Okay, so starting from S, if you move to any neighbor, then you have to remove one of these outside nodes, and that is not going to be a vertex cover anymore. So therefore, S does not have any neighbors which are also vertex covers. So therefore, S is a local optimum. Okay, but of course, S is not the global optimum, because the global optimum would just pick the center node, right? You don't want any of the side nodes. Okay. All right, and likewise, if you look at these other examples, so I'm not going to go through them in detail, but in the second example, you have a bipartite graph, And a local optimum would be that you can pick all of the nodes on the right-hand side. So let's say the right-hand side is larger than the left-hand side. Okay, then the right-hand side is actually a local optimum. And again, the reason is because if you pick all these nodes on the right-hand side, okay, then if you want to look for a neighbor of this solution, so let's say that this is your current solution S, okay, then a neighbor of this solution, you would have to take out one of these nodes. Okay, but as soon as you take out one of the nodes on the right, then you're not going to cover the entire graph anymore. So again, S does not have any neighbors, which are also vertex covers. And so S itself is a local optimum. Okay. But the global optimum would be to take the nodes on the left. Okay, and likewise for this final example, a local optimum is that you take so out of every 3 nodes, you take 2 of them. Okay, so this you can check is a local optimum, but this is not a global optimum because a global optimum is that you take every other node. Okay, you take like every other node. All right, so the point of this is to show you that gradient descent is not necessarily going to find you optimal solutions to problems. Okay. All right, and so just to summarize all of this stuff, so local search, right? So we just saw an example of local search to solve vertex cover. And in general, local search means that we're considering an algorithm which looks at a bunch of possible solutions. Okay, so I'm drawing a bunch of points, and they represent possible solutions to a problem. And also, we have some sort of topology or graph defined on these possible solutions. Okay, and this graph represents the neighbor relationships between these solutions. So, for example, this guy has 3 neighboring solutions. And local search just means that you're going to start at some node, and then you can go to any of the neighboring solutions. Okay, you can only go to you can go to one of these neighbors, but you cannot, for example, go 2 hops away. Okay, you can only go 1 step at a time. And gradient descent is to you basically look at all these neighbors, and then you look if any of them improve on the solution, then you go towards that neighbor. So it's kind of gradient descent is basically a greedy algorithm, okay? Because you just look at 1 step ahead, and then anything that can improve locally, you can possibly accept that step. Okay. And as we saw, gradient descent doesn't always find the optimum because, for example, if you're in this situation, okay, so here what I mean is that you have a bunch of possible solutions like this, right? But if you apply gradient descent, then you're going to end up, so if you start over here, you're going to end up at this solution. And once you get to this solution, you're never going to leave because all of the neighboring solutions, okay, so these are the 2 neighboring solutions, and they're all worse than this solution. So therefore, you're just going to get stuck at this solution. And of course, this is not the optimal solution because the optimal is over here. Okay, so that's local search, right? So so it's a useful algorithm because it's very easy to implement, okay? But it can get stuck in these local optima. So what can we do about this? Okay, is there any way to improve local search? Okay, so now we're going to talk about this algorithm called the Metropolis algorithm, which is a way to improve local search so that it does not have to get stuck at these local minima. Okay. So the way the Metropolis algorithm works is that, so if you just look at basic local search or basic gradient descent, okay, Metropolis is a way to improve gradient descent, okay, and gradient descent is a form of local search. Yeah, so Metropolis is a improved form of gradient descent. And the way it works is that if you just look at basic gradient descent, then once you get to the to a local optimum, you can never move out of that local optimum because all of the neighbors have worse objective values. Okay. However, for the Metropolis algorithm, what you allow yourself to do is that you allow yourself some probability to move to a neighbor with higher objective value. Okay. In gradient descent, you always move to neighbors with lower objective values. But in the Metropolis algorithm, you can move to a neighbor with worse objective value, but only with a small probability. Okay, so maybe with some small probability, I can move to this neighbor. Right? And then once I move to this neighbor, then I'm basically out of this little valley over here, and then I can continue gradient descent, and then maybe eventually I can end up at this global optimum. Okay, so Metropolis gives myself gives the algorithm some probability to leave these local minima. Okay, so yeah, so Metropolis. So the reason it's called Metropolis, it's I'll just mention this. It's actually named after one of the authors. Okay, so it's not having to do with like cities and stuff. It's just one of the authors is actually called Metropolis, right? And these guys. So this algorithm is quite old. It comes from the 50s. Okay, so this was back when they were trying to build thermonuclear bombs, actually. Okay, so this guy Edward Teller, he's actually one of the inventors of the hydrogen bomb. Okay, so just to mention that history. All right, and so the Metropolis algorithm is it's trying to so the intuition for the algorithm is to mimic a physical process. Okay, now in a physical system, so for example, you might have so a physical system typically has some sort of energy. Okay, so if you consider like ice, okay, so ice is some sort of crystal, and I don't know what crystal structure it is exactly, but let me just draw some sort of arbitrary crystal structure. Okay, yeah, so then you have a bunch of, let's say, water molecules, okay, and they're somehow like connected to each other. Okay, and so this configuration of the water molecules has some sort of energy associated with it. Okay, so for example, if the molecules are too crowded together, okay, if they're too close to each other, then this is since the molecules want to repel each other, then this is a very high energy state. Okay, and the system does not want to stay in these high energy states, because if these molecules are repelling each other, then if you just let the system sort of behave naturally, then these molecules are going to spread out more, and as they spread out, they're going to go to a lower energy state. Okay, yeah, so basically there's some sort of energy associated with a state or configuration of a physical system. Right, and it turns out that for many physical systems, so each of these states has a probability of existing. Okay, so even this high energy state, there's some probability that you're going to find you're going to find your system in this high energy state. Okay, but it's a low probability because this is a abnormal state. Okay, the system does not want to stay in this state. Okay. Whereas for this low energy state, right, there's a higher probability you're going to find it in this low energy state. And in fact, the probability that you find a system in a certain state is proportional to this expression over here. Okay, it's exponential in negative of the energy. Divided by this constant K times this T, which is a temperature. Okay, so I'll talk more about the temperature later. Okay, but what you can see from this is that, if you have a very low energy state, right, so so if your E here is 0, right, then you have a high probability of being in that state. Whereas if you have a large E over here, a high energy state, then you have a low probability of being in that high energy state. Right. And the other parameter here is T. Okay, so T is like the temperature, and what happens is that if T is very large, okay, then basically all of these states have roughly the same probability. Okay, because if T is large, then even so if you have like E over here, okay, so you have one state with, let's say, energy is let's say 5, right, and the other one is like 100. Okay, but if T here is a very large number, right, let's say T is equal to like 100, okay, then after you divide by KT, then these two states have roughly the same exponent. Okay, so therefore they have roughly the same probability. And on the other hand, if you have a very small t, right, if t here is like, let's say 1, right, then you can see that the first low energy state is going to have a much higher probability than the high energy state. Okay. Yeah. So the probability of finding your system in a state is controlled by both the energy and the temperature. Right, and now the Metropolis algorithm, the way this works is that, first of all, we're going to fix some sort of temperature, T, okay? And then now we're going to run some sort of modified gradient descent. And what we do is that, suppose you're currently in the state S, okay? Then just like in gradient descent, you're going to consider any neighbor of S, any neighbor S prime of S. Okay, so here n of S means the neighbors of S. Okay, And now if, so you're just going to randomly select one of these neighbors, S prime of S. And now if S prime has lower energy than S, so what we're trying to do is to move to the lowest energy state, okay? And yeah, I forgot to say that. So we're trying to move to the lowest energy state, and the idea is that the energy in a system is going to correspond to the objective value of your function, okay? So here, let's say that we're trying to minimize some sort of function, okay? And so we're gonna make an analogy where the system has some sort of energy and the function has an objective value, and the lower the energy we can achieve, that corresponds to having a lower objective value for the function. Okay. So therefore, we're always trying to move to lower energy states because that's going to decrease our objective value. Okay, so then right here, if you have a neighbor with a lower energy, right, then you can go to that neighbor, just like in gradient descent. However, if you happen to pick a neighbor with a higher energy, okay, then there's a probability that you can still move to this neighbor. Okay. And the probability is going to be like this, okay? It's going to be e to the this exponent over here, and here this delta E term is the change in the energy. Okay, so for example, if S here has an energy of like 10, right, and this new state has an energy of like, let's say 15, okay, then if you go to S prime, you actually increase your energy by 5, and this is normally bad, right? However, in the Metropolis algorithm, you still allow yourself to make this bad move, okay? Because if you make a bad move now, then there's a potential that you can make good moves later, okay? Just like, you know, if you look at this this situation here, right? If you make this bad move right now, it allows you to make much better moves later, okay? So therefore, you allow yourself some probability of making this bad move. However, the worse this move is, okay, so this delta E, the larger delta E is, the worse this move is. And the worse the move is, the lower the probability you make that move. Okay, so if you have to move to a neighbor with much, much higher energy, then you give yourself only a very small probability of making this very bad move. Okay, so that's the algorithm. Any questions about this algorithm? All right, and then what the authors showed was that so they proved this theorem, which said that if you follow this Metropolis algorithm, okay, so if you just run this algorithm, and then if you run it for many, many steps, let's say t steps, okay, then if you look at then if you look at how often you're in different states, okay, so you can consider many different states S. Okay, so f sub s of t is that if you run the algorithm for t steps, how many times are you in state S? Okay, so like so you run this for 100 steps and you're in some state 10 times. Then f of s is 1/10. Okay, right. And what they showed is that if you run this Metropolis algorithm, then the probability you're in a certain state, or the fraction of time that you're in some state S, okay, it's exactly proportional to this Gibbs distribution, to the Gibbs-Boltzmann distribution that we wanted. Okay, so Gibbs-Boltzmann is this distribution, which said that for a state with energy E, you should be in the state with this probability. And then if you run the Metropolis algorithm, then this says that you're going to be in a for whatever state S, right? If you look at the energy of state S, then you're going to be in state S with this probability, right? So the fraction of time that you're in the in state S is equivalent to the probability that you're in state S. Okay, and then you have to multiply by this 1/z here, and 1/z is simply the normalization constant, where you look at all possible states and then you sum up all of their probabilities. Okay, oh, sorry, there's a typo here. So this should be just you sum up over all possible states. Okay, yeah. Okay, so therefore, what this shows is that this Metropolis algorithm basically achieves the Gibbs-Boltzmann distribution. Okay. If you run the Metropolis algorithm for many, many steps, right, then you're going to end up in each state with exactly this probability, which is exactly what you want from the Gibbs-Boltzmann distribution. And this shows you that, so this means that if you run the Metropolis algorithm, right, then this will eventually have a very high probability of achieving these global optima, because the global optima have the lowest energy states, right? And if you the Metropolis algorithm says that you're going to end up in these low energy states with the highest probability. Now, one problem with this Metropolis algorithm is that it's still possible to end up in these higher energy states, right? Because you see that if you plug in a high E over here, right, there's still some positive probability that you end up in these high energy states, which are not global optima; they're local optima. Okay, so therefore we also we want to improve this Metropolis algorithm so that we basically only end up with in the low energy states, in the minimum energy states, which are the global optima. Okay, and the way we can do that is to add something on top of Metropolis, which is this technique called simulated annealing. Okay. And so simulated annealing is that, now in the Metropolis algorithm, we use a fixed temperature T, okay? Right, and in simulated annealing, what you're gonna do is you're gonna start with a large temperature T, okay? And then gradually you're gonna, you're going to decrease T over time, okay? So so the Metropolis algorithm, you have to run it for many steps, right? So if the x-axis here is how many steps you've taken, right? And then the y-axis is your temperature, then you're going to start with a high temperature initially, right? But then you're gonna decrease it over time. Okay. And the basic idea over here is that since initially you have a very high temperature, okay, then that means that initially basically all of these so when you have a high temperature, then basically all the states have the same probability, okay, right? Because we do this E divided by KT term, and if T is high, then almost all the states have the same probability, okay? So if you have a energy landscape like this, okay, then if you use a high temperature, then that's going to basically flatten out all the valleys so that it looks much flatter, okay? It looks more like that. Oh, that's not a good drawing. Okay, so let me, yeah, so it's going to look like something like that, okay? Yeah, so this is with a high temperature, okay? And then the thing about here, so if you have a energy landscape like this, then when you run gradient descent, right, you can basically end up at any of these valleys, okay? Because you're just trying to move downwards, and it's easy to, because these little hills are small, it's easy to jump over these hills when you run Metropolis, okay? And so that means that you allow yourself to easily be able to not get trapped in these local minima, right? If you're trapped over here, you can easily jump out of these local minima, and you can end up at these global minima. Okay, but then eventually you're going to move to lower temperatures. Okay, so when you move to lower temperatures, right? So here, let's say this is temperature, right? So if you move to a lower temperature, then what that's going to do is that's going to magnify all of these valleys. Okay, that's going to make these valleys sort of steeper. Okay, yeah, and then if you make these valleys very, very steep, okay, then it's very hard to jump out of these valleys. So if you run Metropolis in this very steep landscape, then once you get to the local optima, you're going to local optimum. Oh, sorry, the global optimum. Okay, once you get to the global optimum, you're going to stay there. Okay, so the idea with changing the temperature from a high temperature to a low temperature is that initially you want to give the Metropolis algorithm the freedom to jump out of these local optimum so that you can end up at these global optimum. But then later on, you're going to lower the temperature so that once you arrive at this global optimum, then you're going to stay there. Okay, because we're going to make the temperature so low that it's going to make this valley be super, super high. And so once you get to the bottom of this valley, the Metropolis algorithm will never climb out of the valley. It's going to have a super low probability of getting out of that valley. Okay, all right, I just noticed that there's a question over here. So let me read this question. How many iterations may be required? Quick question, how do we do normalization on the states as opposed to neighbors? Right. Yeah. I'm sorry. Oops, where is it? Over here. Well, yeah. So this normalization constant is actually hard to compute. Okay, but when you run this Metropolis algorithm, you don't need to compute the normalization constant. Okay, you simply run this algorithm, and what you can prove is that it's going to end up in these states with these exact probabilities. Okay, but the only thing that you care about is the proportional probability between different states. Right. So if you look at two different states, S and S prime, and then you divide their probabilities, then this 1 over z term is going to cancel out. Okay. So in practice, we don't need to know what the z value is. So even if it's hard to compute, that's not a problem. Okay. We only need to know about the relative probabilities of different states, because all you want to ensure is that you end up at a low energy state with high probability. Okay, and for the first question, for Shicheng's question, so this Metropolis algorithm, it's not really well defined the way that I framed it, right? Because the answer is that we don't know how many iterations it'll take. Okay, you just basically keep running this algorithm until you're satisfied with the answer that you have. Okay, so once you end up in a state that you're sort of happy with, then you can stop the algorithm. Okay. And also, I didn't say how, when you do simulated annealing, okay, I didn't say how exactly you decrease the temperature. Okay, so the rate at which you decrease the temperature, this is called the temperature schedule. Okay, and you can use, or the cooling schedule. Okay, and you can use many different possible cooling schedules, and some of them will work better than others. Okay, and also different problems require different cooling schedules. Okay. So a lot of this, just like, gradient descent is not guaranteed to work always, then Metropolis and also simulated annealing, these are just heuristics, and they're not guaranteed to produce optimal solutions in all cases. Okay. However, if you can somehow tune this cooling schedule correctly, then you can usually get pretty good solutions using the Metropolis algorithm with simulated annealing. Okay, so it's a heuristic, and it doesn't give you any guarantees, but in practice, it tends to work pretty well. Okay, any other questions about this? Page 5, if we choose all the nodes, it's still local optimum, right? Page 5. Are you talking about the first one? If you choose all the nodes, then you can actually take out one of the nodes, right? So if you choose all the nodes, you can take out the center node, and that's still vertex cover. So that would not be a local optimum, right? However, if you just take all the nodes on the side, right, that is a local optimum, because you cannot remove any node from the solution and still have a vertex cover. Okay, any other questions? Oh, right. And for all these other graphs, if you take all the nodes, okay, those are not local optimum, because you can take, for example, in this bipartite graph, right? If you take all the nodes, then you can remove some of the nodes and still have a solution, right? And then, and in fact, you have a better solution because you have fewer nodes. So therefore, these are not local optimum. Okay. So the only local optimum are where you end up at a state where you cannot remove any more nodes. Okay. And those are the local optimum. Okay, so all right. So then, if there are no other questions, I'm going to move on to the next part, which is that we're going to look at a particular local search algorithm, which is going to solve a problem on these things called Hopfield neural networks. Okay. So so I'm not going to give too much of a background on these Hopfield networks. In fact, I don't even know that much about them. But basically, what it is that so the Hopfield network is a graph. Okay, so the network refers to a graph structure. Okay, and the graphs. So for example, you can look at this triangle down here. Okay, and the graphs. Each node has two states. You can call them like plus or minus one. Okay, and the Hopfield network can encode some information in the graph, right? So by setting these different nodes to be plus or minus one, you have different configurations of this network, and then these can encode different states. Okay. And these states kind of correspond to like remembering certain things. So the Hopfield network can actually memorize certain patterns. Okay, and this is how they're used in like machine learning. Okay, but in any case, what we're trying to do over here is that, so we're not going to really study Hopfield networks. Okay, instead, we're going to look at a local search algorithm which is used to optimize these Hopfield networks. And so what we mean by optimize is that, so again, we're going to set each of these states to be plus or negative 1. Okay, so a configuration is to assign a value to all of these nodes. And furthermore, between any two nodes, we have these edges. Okay, and the edges can, we have these edges, and the edges have weights on them. And the weights can either be positive or negative. Okay, now in this example, they're all positive. Okay. And the meaning of the edge, or the weight on the edge, is that if you have a positive number, okay, then you actually want the two endpoints to have different states. So for example, since you have a 7 over here, right, then you want maybe this state, this node, if it's 1, then you want the other node to be negative 1. Okay, and then the 6 over here, this again means that you want the two endpoints to have different states. Okay, so since this top one is 1, then you want the bottom one to be, the top one is negative 1, you want the bottom to be 1. Okay, and then this 5 again means that you want these two endpoints to have different states. Okay, but here, we're forced to set both of these guys to 1, both of the nodes to 1. And so this means that, we have all of these constraints which are imposed by these edges, but it's not possible to satisfy all the constraints simultaneously. Okay, there's no way to choose values for the nodes to satisfy all of these constraints simultaneously. Okay, and what we're trying to do with a Hopfield network is to, if I give you a network with all of these edge weights, right, we're trying to satisfy as many constraints as possible. Right, so this is an optimization problem on the Hopfield network. Okay, you're going to choose states for the nodes to satisfy as many constraints as possible. Okay, so let me be a bit more precise about this. So actually, for our algorithm, we're not going to satisfy as many as possible. We're going to instead look for something called a stable configuration. Okay, so let me say what a stable configuration is. So first of all, if you have an edge, okay, so if this edge is satisfied, then you say it's a good edge, and otherwise you say it's a bad edge. Okay, and so again, what we mean by satisfied is that, so for example, over here, right, if you look at this edge over here, right, so here you have a positive weight, and the endpoints are different states. Okay, so let's say white means 1 and black means negative 1, right? So since you have a positive weight on this edge, you want the endpoints to have different states, and so this edge is satisfied right now. Okay. Now, on the other hand, if you look at this edge, right, so this edge has a weight of negative 5, right? And when you have a negative weight edge, you want the endpoints to have the same state. Okay. However, here the endpoints have different states, and so this edge is not satisfied. Okay. So yeah, so this is a good edge, right? This one is good, and the bottom one is bad. Okay. Right. And then also you can say that a node is satisfied if, so for example, if you look at this node, okay, it's got 4 neighboring edges, right? These 4 edges, okay? And some of them are satisfied and some of them are not satisfied, right? So for example, or some of them are good edges. So this is a good edge, this is a good edge, right? This one's good, but this one's bad, okay? So now if you add up the weights of all the good edges minus the bad edges, okay, then if this is positive, then you say that this edge, this node is satisfied. Okay, or sorry, if it's negative. Okay, so yeah. So for example, here, right? Since you satisfied this edge, you get like 4 points. Okay, and since you satisfy this edge, or since this edge is good, you get 1 point, right? And you get 1 point over here, right? But then you lose 5 points over here. You lose 5 points over here. Okay, so altogether, right? You have 1 point, right? And as long as your total number of points is positive, then you say that this node is satisfied. Okay, Yeah, so we have one satisfied node in this configuration, and let's look at some other node. Okay, so this node, let's see. So this node is not satisfied. Okay, because this is a bad edge, and this is a good edge. Oh, wait, sorry. This is a good edge, right? Yeah. So negative means all right. So this node is also satisfied. Okay, and what about this node? Right. So I guess in this case, all the nodes are satisfied. Right. Okay. Yeah. So so what we're gonna do is to look at all of the nodes and see if each of them is satisfied. Okay. And if you have a configuration where all of the nodes are satisfied, then you say this is a stable configuration. But if you have a configuration where some of the nodes are not satisfied, okay, then it's not stable. And so, so the problem we're trying to solve is, can you find a stable configuration for the Hopfield network? Now, in fact, it's possible that there is no stable configuration, right? Because if I just give you like arbitrary weights on the edges, right, how do we know that there exists a stable configuration? Well, it turns out that there is always a stable configuration, okay? And in fact, we're going to look at an algorithm which produces a stable configuration. Okay, so the way that we prove that there is a stable configuration is that we're going to give you an algorithm which actually, when it terminates, it will end up with a stable configuration. And furthermore, we're going to prove that this algorithm always terminates. Okay, and so the algorithm is very simple. It's just this algorithm over here, which is that you start from an arbitrary configuration. Okay, so you just set the nodes to plus or negative 1 arbitrarily. And then you look at whether your current configuration is stable. And if it's not stable, right, then that means that there's some unsatisfied node, right? So remember, satisfied means that you add up all of these weights around the, you add up the weights of all the edges around the node, and that's positive. Okay, that's satisfied. And if the sum is negative, then you have an unsatisfied node. So if you have an unstable configuration, that means that there is some node which is unsatisfied. Okay, so then you can just pick any unsatisfied node. And then what you're going to do is you're going to flip the state of that node. Okay, so the node is currently 1, you make a negative 1. And if it's negative 1, you make it into a 1. Okay? And it's going to turn out that once you flip this node, then this node is going to go from being unsatisfied to being satisfied. Okay? And then it turns out that if you keep running this algorithm, so as long as you have a non-stable configuration, you keep looking for unsatisfied nodes and then flipping them. Okay, and then if this algorithm eventually terminates, then this solution it returns is guaranteed to be stable, right? Because if it's not stable, then the algorithm will not terminate. It will keep running until you end up with a stable state. So if we can prove the algorithm terminates, then it's guaranteed to be stable. The solution is guaranteed to be stable. Okay. Okay, so then how can we prove this algorithm? Well, okay, so before we prove the algorithm terminates, let's first do an example of this. Okay, so the example is that so suppose you have a network like this, right? And so initially you you set the node values arbitrarily. Okay, and then that's gonna produce an unsatisfied node over here. Okay, because for example, here you have a negative weight, so you want these two nodes to have the same color. Okay, but they don't have the same color, so you're going to lose 10 points over here, and then here you gain 8 points, but altogether this guy has he's got negative 2 points. Okay, so he's unstable, or sorry, he's not satisfied. So because he's not satisfied, then we are going to flip his state from black to white. Okay, right. So then after that, so the thing to notice is that once you flip his state, okay, then he goes from being unsatisfied to being satisfied, right? Because now, once he becomes white, then you can see that how many points does he have? Okay, he gains 10 points over here, right? Because he satisfies this constraint, right? The negative 10 means that these two guys should have the same state, and they do have the same state, so you get 10 points. Okay. Now this 8 means that these two endpoints should have different states, but they have the same state. So then you don't satisfy that constraint. So you're going to lose 8 points. Okay, but altogether, this guy has positive 2 points. right? He used to have negative 2 points, and now he's got positive 2 points. Okay. So yeah, so he's gone from an unsatisfied node to being a satisfied node. All right, but we're not done yet because in this new graph, there are still unsatisfied nodes. So for example, this node over here is unsatisfied, right? Because this negative means that these two endpoints should have the same state, but they have different states right now. So so therefore, we're going to flip this guy. We're going to flip this one to make him white. Okay, and once you flip this guy, then now that's going to cause this center node to become unsatisfied. Okay, so you can check that this node is unsatisfied. Okay, so then you can flip him, right? And then that's going to cause this node down here to be unsatisfied. So you flip him, and then you just keep going like this. But then eventually we're going to end up with this state over here, and this is a stable state. Okay, you can check that all of the nodes in this situation are satisfied. Okay, all of them have positive points. Okay. All right, so that's the algorithm. Okay. And so what we have to show is that if you start from any arbitrary initial configuration, then eventually you're going to end up with a stable configuration. Okay. Okay. So the way we're going to do this, the way we're going to prove this is that, okay, yeah. So the theorem is that this algorithm is going to terminate, and the number of iterations that it takes to terminate, okay, is going to be at most the sum of all of the edge weights, right? The absolute values of the edge weights. Okay, so if you go over here, right, if you add up all the edge weights, their absolute values, then you have like 10 plus 8 plus 4 plus 2 down here. So whatever that is, okay, 20 something, 26. Okay, that's how many iterations it takes in the worst case to terminate. Okay, so then how do we prove this? Well, what we're going to do is we're going to create this thing called a potential function. Okay, and this potential function basically measures how much progress we've made towards termination. Okay, so the larger the potential function, the more progress we've made towards termination. Okay. All right, and the way this potential function is defined is that in any configuration S, you're going to look at all of the good edges, okay, the satisfied edges. And then you're going to add up their weights, the absolute values of their weights. Okay, and then yeah, and this is a measure of how good the state S is. Okay, and now this measure, this phi value, right? So obviously it's not going to be more than W, right? Because W is the sum of all of the edge weights. Okay, and furthermore, we're going to show that this phi value increases by at least 1 after each step of the algorithm. Right. So each step of the algorithm, you're going to flip some node, right? Because each step of the algorithm, you find some unsatisfied node, and then you have to flip him. Okay. And we're going to show that each time you flip one of these unsatisfied nodes, your phi increases by at most 1. Okay. So since your phi is always non-negative, and since the phi can never exceed W, then if you run for at most W steps, right, then this phi will be equal to W, at which case the algorithm has to terminate. Because phi can never exceed W, and because it increases by 1 after each flip, then after at most W flips, the algorithm will terminate. Okay. Right, so the way to show that this phi increases after each flip is that what we saw was that, so over here, if we go back to this example, okay, so when you flip a node, so for example, when you flip this node, okay, then previously this was a good edge, right? And this was a bad edge. Wait, is that right? Yeah. Wait, I keep sort of forgetting which way this goes. Yeah. So if it's negative, yeah. Oh, sorry. If it's negative, they want to have the same state. Oh, okay. Right. Sorry. So if it's negative, you want to have the same state. So this was a bad edge, right? Yeah, and then this was a good edge. Okay. Okay, sorry, I got confused there. Yeah, I keep messing up like which edges are good or bad. Okay, because it's kind of weird how they define this. Like if it's a negative weight, then you actually want these two guys to be the same. Okay, you want them to have the same state. Right, but anyways, yeah, so this is So overall, this node is not satisfied, right? Because you lose 10 points over here and you only get 8 over here. But after you flip this node to a white node, okay, then you can see that this node now, all of the bad edges, this is now a good edge, right? Because now, because you have a negative 10 over here, you want both endpoints to have the same color, okay? And then over here, this edge, which used to be a good edge, this now becomes a bad edge. Okay, so you can see that once you flip a node, all of the good edges become bad, and all of the bad edges become good. Okay. And now let's look at how phi changes after you do one step of the algorithm. Okay, so when you go from step S to step S prime, what happens is that the phi value in S prime is equal to the phi value in S, and then the only change between S and S prime is if you flipped this node U, right? Then it's got a bunch of neighbors, and all of the good ones became bad, and all of the bad ones became good, right? So if this is also bad, it became good, okay? And now what we know is that the reason you flipped U is because it was an unsatisfied node, right? So that means that if you add up all the good points and you subtract all the bad, if you add up all the good weights and you subtract all the bad weights, right, then this is a negative value, right? Because overall, this is an unsatisfied node. So if you add up all the good edges and you subtract all the bad edge weights, then you get a negative value. Okay. However, now that you flip U, okay, then all of the good edges become bad and all the bad edges become good. And so now you've actually you've increased this phi, right? Because all of the like if you were losing, let's say you lost 5 points here, okay, and then so initially, let's say you got 5 points over here, right, and then you lost 3 points over here, right, and then you lost let's say 4 points over here, okay. Then after the flip, this is gonna become a bad edge, so you're gonna lose 5 points here, but you're gonna gain 3 points here, and you're gonna gain 3 points here, okay. So altogether, you've actually improved your score, right, because now it's you've improved your score. Okay? And so this shows that after you do a flip, you actually increase your overall score, right? Because the score around U increased and the score for all the other nodes did not change. Okay. And so every time you do a flip, you're going to increase your score by at least 1, right? And so this shows that after each flip, your phi increases by at least 1. And so that means that after W flips, you're going to end up with after W flips, this algorithm has to terminate. Okay. All right. Any questions about this? Okay. Right. So then I'm going to move on to the I guess there's a few more things to say about this, which is that, so what we showed is, let's see, so here we have a decision problem. Okay. So there are two questions you can ask about this this Hopfield network. Okay. One is to find a stable configuration, right? And one is to say, does there exist a stable configuration? So the algorithm we just looked at, it actually answers both of these questions. Okay. Because we know the algorithm always terminates, and when it terminates, it finds a stable configuration. So therefore, there is always a stable configuration. Okay, so the answer to the second question is always yes. Okay, and for the first problem, we actually did find a stable configuration. However, the amount of time that this algorithm takes might not be polynomial, because you need to run for this number of iterations. Okay, so this is like the sum of all of the edge weights, and this is not polynomial in the input size, because if you want to have a polynomial time algorithm, then you need the running time to be polynomial in n, which is the number of nodes, and then log of w, log of the weights. And currently we have an algorithm which is polynomial in n and w. Okay, so yeah, so apparently there is currently no known polynomial time algorithm to find a stable configuration. Okay, and for the second problem, there is a polynomial time algorithm because the answer is just yes, always. Okay, so then I'm going to move on to the next problem. So this is going to be called, so this is the maximum cut problem. Okay, so to introduce this problem, so we talked about the minimum cut problem earlier, right? So a cut problem is basically you have a graph like this, and then you want to cut it into two pieces, A and B. Okay, so and then you're going to look for all of the edges which cross, from A to B. Okay, now in this case we're going to look at an undirected graph. Okay, so we're not going to look for edges which cross from A to B. We're just going to look at any edges which go between A and B, okay, because we don't have directions in this undirected graph. Okay. Now, in the minimum cut problem, what you want to do is to minimize. So each of these edges has a weight, and for the min cut, you want to minimize the sum of all of the weights. Okay. Now, for the max cut, it's just the opposite. You want to maximize the sum of the edge weights. Okay, so yeah, so the only difference, so it's exactly the opposite of the min cut problem. Right. Now it turns out that once you try to maximize the edge weights, then there is no polynomial time algorithm to solve this problem. Okay, so max cut is actually an NP complete problem. In contrast to min cut, which we can do in polynomial time. Okay. And also, like, just in terms of an application for this problem, right? Like, why would you want to maximize the cut, right? For min cut, we want to maybe solve a max flow problem. So naturally, we want to find the minimum cut. But why would you want to maximize the cut? Okay. So one application is that so this is not the applications down here. Okay. I'll just give you another sort of real life application, which is that in like a parallel computing setting, right? So you might have a bunch of tasks that you want to do. Okay, so this graph represents a bunch of tasks. Okay, and the weights between and the weights on the edges represent like communication between the tasks. Okay, and now you want to solve all these tasks in a parallel way. So suppose you have two processors, A and B. Okay, so you're going to give some of these tasks to A and some of these tasks to B. Okay, however, whenever you have an edge, then this means that you have to do some communication. I said this wrong. Okay, so this actually represents a graph, and these edges are like the amount of communication you can do between these two nodes. Okay, and so if you split this node up, then if you split all the nodes up into two parts, right? Then you want to have these two parts be able to maximize the amount of communication they can do. Okay, because these two parts are going to work independently of each other, but occasionally they need to talk to each other. So you need to send information across these edges, right? And you want to maximize the bandwidth between these two parts so that you can do the communication as efficiently as possible. Okay. So if you're allowed to cut up this network in any way you want, well, subject to some constraints like A and B have to be balanced with each other. Okay, but anyways, you want to cut this graph up, and then you want to maximize the amount of communication bandwidth between the two halves. Okay, and so that corresponds to maximizing the cut. Okay, so that's one application of the max cut problem. All right, so somebody is asking, can we flip the sign of the edges and do, no, you cannot do that because so all of these things have positive weights. Okay, so you so both for min cut and for max cut, the graph has positive weights on all the edges. Because, for example, for min cut, it doesn't make sense to have a negative capacity, right? Yeah, so we're always considering graphs with positive edge weights, so therefore you cannot flip the edge weights. Okay, so that's the max cut problem. Okay, and now we're going to look at a local search algorithm to solve this problem. And so the way this algorithm works is that oops, I want to move this thing over. Okay, well, never mind. Okay, so what we're trying to do is to look for these improving nodes. Okay, and what I mean by that is, suppose you've got a graph and you've cut it into two pieces. Okay, and then let's say you have a node over here. Okay, so so say that this node is connected to like this. Okay, so you got A and B over here, and this node X is connected to two nodes on the left and one node on the right. Okay, now suppose you move. So let me just redraw this graph. Okay, now suppose you move X to the other side, to B. Okay, then what's going to happen is let's label all these nodes. Let's call them A, B, C. Okay. Then X is going to be C over here, right? Then what it's going to look like after you move X to the other side is that so currently you have one cut edge from X to C, right? And you have these two other edges from X to A and B, but they are not cut. And now once you move X to the other side, then this cut edge from X to C becomes not cut. And the uncut edges from X to A and B become cut edges. Okay. So therefore, you've improved your cut. You've increased your cut by 1. Okay. And so this, so therefore, this X node is an improving node because by moving this node from one side to the other, right, whether it's A to B or B to A, right, then you can increase the size of your cut. Right. So those are improving nodes. So so this algorithm that we have is that you have a current configuration S, okay, and then you look to see if there are any improving nodes. Okay, so you look at all of your nodes and see what happens if I move the node to the other side of the cut. Okay, is that going to increase my cut? Okay, if there is an improving node, then you're just going to move this improving node to the other side, and that's going to increase your cut. Okay. And if there's no improving node, right? So for all the nodes, if you move the node to the other side, you actually decrease your cut or do not change your cut, then you're going to terminate the algorithm. Okay? Right. So yeah, so we're going to look for these improving nodes, and then you're just going to move it to the other side if you can find an improving node. And if you cannot find an improving node, then you terminate the algorithm. Okay, so yeah, so now let's try to show that this algorithm, let's analyze this algorithm. Okay, so this algorithm is not necessarily going to produce an optimal, a maximum cut. Okay, however, what we're going to show is that when this algorithm terminates, okay, so first of all, we'll show that eventually this algorithm does terminate. Okay? And furthermore, when this algorithm terminates, it's going to return a cut which is at least half the size of the optimum. Okay, so we're trying to return a cut which is as large as possible. Right. So let's say the maximum cut is let's say 100. Okay, then when this algorithm terminates, it's going to produce a cut which has weight at least 50. Okay, so if you sum up all of the cut edge weights, right? So if you have like this, if you sum up all the cut edge weights, that's going to be at least half of the optimum. And in fact, you can say something stronger. You can say that the weight of the cut edges is going to be at least half of the weight of all of the edges. Okay, and of course, half the weights of all the edges. So if you sum up all the edges, then this is, of course, at least as large as the size of the maximum cut. So therefore, if you can return a cut which is at least half of all the edge weights, then that's going to be at least half of the maximum cut. Okay. Right, and yeah. So now the reason this algorithm terminates, first of all, okay, is because each time you find a node, because it's an improving node, right, then it's going to increase the size of your cut. Okay? And of course, your cut cannot exceed your cut cannot exceed this value, okay, which is the sum of all of the edge weights. Okay? So therefore, if you run the algorithm for this number of steps, then because each step you improve your cut by at least 1, then after you run for this number of steps, your algorithm has to terminate. Okay, it can no longer find an improving node after you run for that number of steps. Okay, so that's why the algorithm terminates. Okay, and now for the other part, which is to show that it produces a solution which is at least half as good as the optimum. Okay, so by the way, this is called a 1/2 approximation algorithm. because the solution that it returns is not necessarily optimal, but it's at least half of the optimal solution. So it's 1/2 approximation of the optimal. Okay. All right. Now to show this, what we're gonna so the proof relies on this property, okay, which is that suppose so when your algorithm terminates, let's look at any node u in A. Okay, so remember you have two sides A and B. Okay. Now it must be that if you so we have this expression over here. Okay, so this expression is basically saying that you have A and B over here, and then you have a node U, right? Okay, so the left-hand side is summing up the weights to all the edges on the left. Okay, so here you're looking at U and all and it's the sum of its edge weights to all of the A side neighbors. Okay, and then the other one is going to be let's see, the other one is B. Yeah. Okay, and the other side over here is that here you're summing up the weights from U to all of the B side neighbors. Okay. And you have to have that the left-hand side here is less than the right-hand side. Okay, because if the left-hand side is actually more than the right-hand side. Okay, so suppose you're in this situation where you know, the left-hand side is actually larger than the right-hand side. Okay, then you can just move U to the other side, and you can actually improve your cut. Right? Because if you move U to the other side, now you can cut two edges, right? And so that improves your cut. Okay. So so when the algorithm terminates, there does not exist any improving nodes. Okay. So when the algorithm terminates, you cannot gain anything by moving U to the other side, and that means that U must be connected to more nodes on the B side than the A side. Right? I mean, not more nodes, but I mean the sum of the connections to the B side must be more than some of the connections to the A side. Okay, and this holds for all of the nodes in A. All right, so now what we can do is we can just sum up this expression. Okay, so because this holds for all the nodes in A, then we can do a sum over here for all the nodes in A, right? And then you can do the same sum on the other side. Okay, and now what you get is that if you look at this sum, okay, so what is this? Okay, this is just looking at this is looking at like all of the edges in the A side, and this is summing up all of their edge weights, right? Because we're taking all pairs of nodes in A and we're summing up their edge weights. Okay, so therefore, yeah, this is what you get. Okay, and oh, sorry. And actually, this is 2 times the sum of all of the edge weights. Okay, and the reason is because when you do the sum, you actually count each edge twice. Okay, so for each edge, you're going to count it once in the UV direction in the sum, and then also you're going to count it again in the V to U direction. Okay, so if you look at this expression, it actually counts every edge twice. Okay, so that's why you so these two things are equal to each other. Okay, and now this other part over here, okay, what is this? Here, let me do it this way. Okay, okay, so this here is actually, I claim that this is the size of the cut that you have, okay? Because what you're doing is you're summing up over all of the U nodes, right? U1, U2, U3, right? And for each one of them, you're looking at all of the connections to the B side. Okay, right? So that's what this thing is over here, right? We're summing up from the A side to all the connections on the B side. Okay? And that's simply equal to the size of your cut, right? Because each time you have a node connected from the A side to the B side, that's part of your cut. Okay, so therefore this thing over here is equal to the right-hand side over here. The right-hand side, when you sum over all the U nodes, is equal to the size of your cut. Okay, WAB is the size of your cut. Okay, so therefore we have the first expression over here. Does that make sense? Okay, and now for the second expression, you can get it in a similar way, okay? Because what we have is that we have that you can just replace this A here with B, right? And by the same argument, we have that when your algorithm terminates, this condition must hold for all of the B nodes. Okay, and because this holds for all the B nodes, then now we can sum up over all of the B nodes. Right? We can sum up both sides over all of the B nodes. And when you do that, then this side is now going to be equal to the sum of all of the edge weights in B times 2, because you count each edge twice. Okay, and then this side, right? This is again going to be the size of all of the cut edges, right? Because you're summing here, U is going to be in B, and then V is going to be in A, right? So the sum of all of those edge weights is going to be the size of your cut. Okay, so therefore we have both of these expressions, both of these expressions. Okay, and now all we need to do is to okay, and now let's look at suppose you add up all of the edge weights. Okay, now if you add up all the edge weights, then you can break the edges into 3 types. Okay, the first type is you have an edge and so you have a graph like this, and you have A and B, right? So the first type of edge is between 2 A nodes. Okay, so you have this type of edge over here. Okay, and the second type of edge is between all the B nodes. Okay, so sorry, there should be a B over here. Yeah, so there are quite a few typos in these notes. So the notes, I actually got them from online, and they have some typos in them. So sorry about that. Okay, so yeah, so these are this type of edge, and these are this type of edge. And the final type of edge is the ones that cross between A and B. Okay, so if you add up all of the edges, then you can break them into these 3 classes. Right? And now, what do we know about these 3 classes? Well, by this first inequality over here, by this first inequality, oh, I'm sorry, computer's doing something weird. By this expression over here, you have that the sum of all of the A to A edges. Okay, this is at most, so we're going to divide by 2 over here. This is at most half of the weight of the cut. Okay, so therefore this thing over here is at most half of the weight of the cut. Okay, and likewise from this expression, if you divide by 2, you have that the sum of all the B to B edges is also at most half of the weight of the cut from A to B. Okay, and then this part is simply the weight of all of the cut edges. Okay, and so this shows you that the sum of all of the edge weights is at most 2 times the cut, 2 times the size of the cut. Okay, and this means that the size of the cut is at least half of the sum of all of the edge weights. Okay, so now we've shown that the size of the cut is at least half of the size of all the edges, right? Which is going to be at least half of the size of the maximum cut. And so this means that this algorithm produces a solution which is at least half as good as the best possible solution. Okay, any questions about this? Okay, all right, so then, right, so there's a few more things I'll say about this algorithm. One of it, so one thing is that this algorithm currently is not polynomial time, okay? And it's because the running time of the algorithm, right? So the only bound on the, let's see. So somebody said, can you solve the min cut in the same way? You can solve min cut, well, let's see. I think you can solve min cut in a similar way, but you wouldn't want to. Okay, because this max cut algorithm has a few problems, right? The first problem is that it doesn't give you the optimal solution. It only gives you something which is 1/2 the optimal. Okay, so whereas for min cut, we have an algorithm which gives you the optimum solution. Okay, and the other problem with this max cut algorithm is that the running time, currently the only bound we have on the running time is the sum of all of the edge weights. Because what we said is that each time you run one of these while loops, you're going to improve your cut by at least 1. Okay, and you know that your cut cannot exceed the sum of all the edge weights, and so you know that the total number of iterations cannot exceed this value, the sum of all the w's. Okay, But again, the sum of all the w's is not polynomial in the input. Right? If you want it to be polynomial, you need the running time to be polynomial in log of w. Okay, so this max cut algorithm is bad because in two ways. One, it's not optimal, and two, currently it's not polynomial time. Whereas for minimum cut, right, we have both. We have algorithms which produce both an optimal solution and they run in polynomial time. So therefore, there's no reason to use this type of algorithm for minimum cut. Okay, so so the final thing, so one more thing we'll say about this max cut is how can you improve the running time? Okay, how can you get it to be polynomial? So what you can do is you can use this big flip algorithm, okay, or big improvement algorithm. And the idea here is that when you choose a node, we're only going to choose nodes which increase the cut value by a large amount. Okay, because previously for this algorithm, right, when you choose a node, so for example, when you choose this x, right, it improves the cut by only 1. And so if your maximum cut is, let's say, 1,000,000, okay, then you might need to take like 1,000,000 of these steps before you can terminate. Okay. However, for the big improvement algorithm, you might say that I'm only going to flip a node if it improves my solution by at least 100. Okay. In that case, if your max cut is 1,000,000, then in 10,000 steps, you're going to terminate. Okay, so that's the big improvement algorithm. Okay, which is that I'm going to say I will only flip a node when I can improve my solution by a large amount. Okay, now how large should I make this improvement? Okay, so what I'm going to do is I'm going to choose an epsilon parameter over here. So epsilon can be anything which is positive. Okay, any positive value. Okay, and I'm going to insist that my node can improve my cut by at least 2 epsilon divided by n times the current weight of the current weight of the cut, the size of the current cut. Okay, so if my current cut is like 100 and epsilon is, let's say, 1%, right? Then I want to improve by at least 2, or well, actually 2 divided by n. Okay. All right. So anyways, yeah. So once you use this big improvement algorithm, then what happens is that each time you run the algorithm, okay, each time you run an iteration, you're basically going to improve your solution by a factor of 1 plus epsilon divided by n, right? Because suppose this thing here is, let's say, 1%. Okay, so then what I require is that I'm only going to take a flip if it improves my solution by 1%. Okay, so therefore, every time I run this algorithm, I improve my cut by 1% by this factor. Okay, and that means that if I run for n divided by epsilon iterations, then my total improvement is going to be this factor to the n divided by epsilon power. Right? Okay, and so how large is this value? Okay, so if you call this thing x over here, if you call x epsilon divided by n x, right, then this is going to be let's call this x, and so this epsilon divided by n is going to be 1 divided by x. Okay, so that means that after you run for n divided by epsilon iterations, you're going to improve by this amount, by this amount. Okay, and this value here is going to be at least 2. Because of this inequality over here. Okay, so that means that after n divided by epsilon iterations, you improve your cut value by at least a factor of 2. And since your maximum cut value is at most w, right, then you can do this stuff at least log w times, right? Because each time you do n divided by epsilon iterations, you improve by a factor of 2. So after log w times, your cut will reach a value of w. Okay, and so that means that the total number of flips you do is going to be log w over here, right, times this n divided by epsilon. Okay, and so therefore the total number of flips that you can do with this big improvement algorithm is going to be this. Okay, and now this is a polynomial time running running time. Okay, because now it's polynomial in log w. Okay. right? So what we gain from this algorithm is that you now have polynomial running time, okay? However, what you lose from this algorithm is that because over here you insist on only taking these cuts which improve your, only doing flips which improve your cut by 2 epsilon over n, okay, then what you can show is that now you don't get a 2 approximation anymore, okay? Instead, you get a, your solution is only guaranteed to be this times the optimal solution. Okay, so for example, if your epsilon here is, let's say, 0.5, okay, then your solution is not going to be half of the optimal solution. It's now only going to be 40% of the maximum solution. Okay. All right. So I'm not going to do this claim for you. The claim is actually very similar to how we did this proof over here. Okay. All you need to do is you need to just replace some of these values over here by the 1 plus epsilon. Okay, so you can try to just do that proof yourself. It's very similar to the previous one. Okay, so yeah, so I'm almost out of time. Okay, so I guess I am out of time. So I'll just say one more, or actually two small things. Okay, so first of all, this local search algorithm. Yeah, so there's another algorithm which is not based on local search, okay, which also gives you a 1/2 approximation. And also the current best algorithm for max cut gives you like something like an 88% approximation. And it's actually been proven that unless p equals mp, you cannot get better than a 94% approximation for max cut. Okay, so if p is not equal to mp, then not only can you not find the optimal solution to max cut, you cannot even find something which is better than 94% of the optimal. Okay, and currently there is an algorithm which finds something which is 88% of the optimal. Okay, yeah, so there's still some gap between what we have and what we potentially can do. Okay. All right, so so I'm out of time, unfortunately. So yeah, I mean, it's kind of weird that we have this new schedule, and so I need to like cut out lots of stuff. So I guess I have to stop the lecture at this point. What I'll say is, I'll just say one thing over here, which is that currently the local search algorithm we have, what we're doing is like one flip. Okay, meaning that each time we take one node and move it from the A side to the B side, or vice versa. Okay. Now, potentially you can get better performance if so you can get a larger max cut if you allow yourself to move more than one node. Okay, and so therefore there's this Kernighan-Lin heuristic which is often used in practice. Okay, it's very effective in practice, and this actually allows you to move a large number of nodes from one side to the other. Okay, yeah, so, and this is also an efficient algorithm. Okay, this is less efficient than just a local search algorithm. I think this takes something like cubic time. I'm not sure about that, but I think it takes like something like n cube time, where n is a number of nodes. Okay, but you have to like check that because I can't remember the exact number. But anyways, the Kernighan-Lin is not too slow. Okay, it's sort of useful in practice. And oftentimes, when you do this algorithm, it can get you a better cut in practice. Okay, there's no proof that it actually improves on the previous algorithm, right? So there's no proof that Kernighan-Lin gets you better than 1/2 approximation. However, in practice, it oftentimes gets you better approximations. Okay, so I guess this is all I have time for. I'm also going to skip this thing about Nash equilibria. Okay, so this is a pretty interesting topic, but it takes more time than I have. So yeah, so if you have any questions about this, you can contact me and we can talk about how this works. Okay. All right. So any questions up to now about any of these stuff we talked about? All right. So in that case, yeah, we're gonna stop the lecture. And then we'll have so somebody does have a question. Page 24. Yeah, right. Sorry. Well, yeah, it'll show that after this number of iterations, you can improve. Well, it depends on what this n divided by epsilon is, right? Because the limit that you gave is only for large x. Okay, so if n divided by epsilon is actually not very large, then the number you get is not going to be exactly like 2.71. It'll be something larger than 2. Okay, so what we need over here is that as long as n divided by epsilon is larger than 1, then this expression here is at least 2. Okay, whereas I guess what you're talking about is for very large x, then we can improve by a factor of actually e, right? 2.7. Yeah. Okay, but actually all we need is that we improve by a factor of 2, because if you improve by at least a factor of 2, then after log w times, then your cut reaches a value of w, in which case the algorithm stops. Any other questions? Okay, so then I will talk to you guys on Thursday. Okay.